All right. In part C, we have x equals 3 cosine theta and y equals 7 sine theta. Here the parameter is theta. Okay, so this is slightly different from part A and part B. In fact, we have x and y represented by trig functions, right? Cosine and sine. So whenever you have x and y involving cosine and sine, it's better to remember the Pythagorean identities because that's what we're going to rely on. And in fact, to get back to the rectangular equation form, but before doing that, we have to choose sample points for theta, sample values for theta to find x and y coordinates of sample points, okay? So what I did here, let me just show you what I did, and I just want to start with 0 for theta and going all the way to 2 pi with the increments pi over 4, but this could be totally different in your case. You may go with like negative pi and pi, or 0 to pi only to see if you can get the full picture here. But again, the whole idea is like to get the full picture with as many points as we can, and the choices of t just all depend on you. Okay, so with my choice of t, I got t equals 0. And when I plug this t equals 0 back in x and y, you get 3 times cosine 0 and sine 0. So you're going to do trig function evaluation, so you better set your calculator into the radian mode so that cosine 0 is going to spit out 1 and sine 0 is going to spit out 0. So you get the point, the coordinates of the point to be 3 and 0. So that means I'm starting right at the right corner here, okay? So this is my starting point based on the choice of t I have here, okay? And the next point is pi over 4, and when you plug in, and you need a calculator to get some numerical values here, right? It's almost like 2.12 and 0.70. Here we go. This is the point, the second point. So as you see, I'm going in this direction. Okay, apparently I'm going in this direction, but without having the full picture, you may not see where you're heading towards, right? You may not see that this is an ellipse, right? So we have to keep adding sample points. Let's go with pi over 2, and when you plug in pi over 2 for t in x and y, so you get 0 and 1. Here we go. I got this top part of the ellipse, okay? Here we go. And let's just keep doing that. Let's go to pi. So that takes you all the way to negative 3 and 0. Okay, in between you have also this point. Now I have like some kind of like a good judgment of what the curve looks like, right? Because I'm going in this direction. So I have a nice half of the ellipse. And but you don't stop here because you don't want to know where it tends to, right? It could be like a parabola as well. We don't know, right? Or it may make a turn after all. So we don't know much about it, right? So because we don't have this part yet. All right. So to sort of like get the full picture, keep going, obviously. Keep going, and then add 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. And interestingly, at 2 pi, you go back to where you start. Okay, so you go back here. Okay, so when you keep adding those, all right, and why do we have this sort of like looping behavior? Because of the properties of trig functions, right? We have cosine and sine. They are 2 pi periodic. In fact, in the background, that was the whole rationale of me picking the length of t interval to be 0 to pi, because I know that these guys are 2 pi periodic, and that would give me like a good picture of the graph within this t range, okay? So in fact, I got it this way, so it's an ellipse. So it's not like, you go like this for the first part, and then you go like this, or you go like that, okay? So to be able to see the full picture, you have to keep, you have to be patient and then check all the points and place them in, and then connect them with a continuous blue curve. That's in fact the ellipse, okay? All right, so let's also find the rectangular equation corresponding to this parametrization. Okay, so what I'm going to do here is to use this known identity to achieve that. So I'm going to use this, and to do that, first I'm going to divide the x equation by 3. So I got cosine theta. And I'm going to divide the y equation by 7 to get the right hand side equals sine theta. Okay, and all I'm going to do is just adding the squares of each other. Okay, squares of these. So x over 3 squared plus y over 7 squared equals 1. That's me using the Pythagorean identity. That allows me to eliminate the parameter theta. Okay, and that's a very nice representation of the equation of an ellipse, right? 3 squared. This is what we covered in the previous section when we were talking about conic sections, right? Y minus 0 squared over radical 7 squared equals 1. So this is an ellipse centered at 0, which is the origin, with A being 3, B being radical 7. So it's almost like a flatter, like flattened ellipse, right? In this direction, it's flattened. You can go ahead and find the eccentricity of that, but we don't need. You can find the vertices, foci, and everything, but we're not being asked for that. All we needed to have is the rectangular equation corresponding to this parametrization, and here we go. I think that takes care of part C already. So, and that makes the end of the video. All right. So if you have any questions or comments, please send those to my way, and please take your time in this setup here to graph parametric equations. All right. Bye.